Hi everybody, in this video I want to do two example problems illustrating how to use the Einstein relative velocity formula. Alright, so here's the first example. Imagine I have a planet, a warship, and a fighter. P for planet, F for fighter, W for warship. Let's imagine I'm taking my positive x direction to the right. And remember that the Einstein velocity formula and also the other relative velocity formulas that we've worked with, we're working with velocity components. So we have to choose a coordinate system and then we have to assign positive or negative values consistent with our coordinate system. So there could actually be a little x subscript on each of these. I've left the x subscript off so that we don't have subscript overload. Okay, so let's say we're given the following information. The velocity of the warship relative to the planet is positive 0.600 c. That means from the planet's perspective, the warship is heading to the right. Let's say that we know that the velocity of the fighter relative to the planet is positive 0.800 c. So relative to the planet, the fighter is moving to the right. Let's say that what we want to find is the velocity of the warship relative to the fighter. Now we can use a little bit of our intuition to try and figure out at least the sign that this should have. From the planet's perspective, the fighter is moving faster to the right than the warship. So the fighter and the warship should be getting further apart. That means from the fighter's perspective, the warship should be lagging behind. So we should end up with the velocity of the warship relative to the fighter that comes up negative. Now, that's as far as our intuition can take us. If we try to use our ordinary relative velocity formula, we subtract these two numbers and say, oh, this thing is fading off to the left at 0.2 c. But that's not going to work. That's the numerator, but the denominator, remember, complicates things. All right, so with regard to actual number, it's hard to have an intuition, but we should at least be able to figure out the sign. Okay, so let's go about using this Einstein relative velocity formula to find the velocity of the warship relative to the fighter. All right, now what I recommend in using this formula is not trying to go, oh, okay, here's the formula, let me figure out what A is, let me figure out what B is, let me figure out what D is, take this formula and map everything. What I recommend is just remembering that the first subscript matches the first subscript here, the second subscript matches the second subscript here, the third, this one has to be the same. So second subscript of the first one has to be first subscript of the second one. All right, and then whatever these are, they go down here. So that's your pattern. So if we want to apply that here, what it means is my first term has to have a W for the first subscript. My second one has to have a F for the second subscript. W, and I'll put a little box plus velocity box, same thing, the fighter, right? First subscript, second subscript, there's our remaining subscript there. Then whatever these are will end up in the denominator, 1 plus, I'll just leave space for them over c squared. So I'll have this one here multiplied by this one there. I'll put those in the denominator soon. Okay, so all we got to do is find our third thing. Because someone might give you a problem with 4 or 5 or 6 things. You need to find a third thing that links these. Well, we've only got 3 things in this problem. The third thing would be the planet. All right, so if I've got the velocity of the warship relative to the planet, and the velocity of the planet relative to the fighter, I'd be in business. And I'll just write these things down here. Velocity of warship relative to planet, velocity of planet relative to fighter. Okay, so let's see if we have these things. Velocity of warship relative to the planet, we have that. That's positive 0.600 c. Velocity of the planet relative to the fighter, we don't actually have that. We have something that's related to that. We have the velocity of the fighter relative to the planet. That's positive 0.800 c. What we want is the velocity of the planet relative to the fighter. Remember, in dealing with relative velocities, if you flip the subscripts, you change the sign. So the velocity of the planet relative to the fighter isn't this, it'll be minus 0.800 c. And just remember to think about this from ground up. From the perspective of the planet, the fighter's closing in to the right. But if we attach our coordinate system to the fighter, the planet's closing in this way, the planet relative to the fighter is moving to the left. That's the real physical origin of that minus sign. Okay, so let's plug these numbers in. Velocity of the warship relative to the fighter will equal, I'll put this first one in, velocity of warship relative to the planet, that's positive 0.600 c, plus, now I need the velocity of the planet relative to the fighter. I'm just going to write that down here. Velocity of planet relative to the fighter will be minus 0.800 c, because we switched the subscript from that. Minus 0.800 c, and then I'll have 1 plus, and I'm not going to put all the zeros, 0.6 c and minus 0.8 c over c squared. Let's work that out. Positive 0.6 c plus a negative 0.8 c will give me minus 0.200 c. And then here I've got c times c over c squared. So those c's will cancel. C squared over c squared gives me 1. I'll have 0.6 times negative 0.8. That'll be minus 0.48. Minus 0.48 plus 1 is 0.52. And there's no units here because the units canceled out. We're adding to 1. All right, so I'm going to have minus 0.200 c divided by 0.520, and that will give me, I'm just going to write that here, minus 0.385 c. That's for the velocity of the warship relative to the fighter. Notice it came out negative, and let's understand that negative sign again. From the planet's perspective, the fighter is going toward the planet faster than the warship. So we should expect, although we can't just add or subtract these numbers simply, that the space between the warship and the fighter should be getting bigger. So from the fighter's perspective, the warship is falling behind. So if you imagine here's an x coordinate, here's a y coordinate, here's my coordinate system. So the velocity of the warship relative to the fighter is to the left, but the positive direction in my coordinate system is to the right. So the velocity of the warship relative to the fighter has to come out negative. We could turn it around, all right? The velocity of the fighter relative to the warship, well, from the warship's perspective, the fighter should be pulling ahead, so we would flip the subscripts. If the velocity of the warship relative to the fighter is minus 0.385 c, the velocity of the fighter relative to the warship would be positive 0.385 c. All right, so hopefully that helps. We could also do lots of other different relative velocities, flipping subscripts just to illustrate this. If I've got the velocity of the warship relative to the planet being positive 0.600 c, I could imagine trying to find the velocity of the planet relative to the warship. From the warship's perspective, the planet is getting ever closer to the warship, so in this coordinate system, the planet's moving to the left. So the velocity of the planet relative to the warship will be minus 0.600 c, again using that flip the subscript rule. All right, so I'm going to erase this, and we'll do one more example. Here we go. Boom. Okay. In the second example, I'm going to change things up. I'm going to have the Earth, a ship, and a missile represented by E, M, and S subscripts, respectively. I'm going to take my positive x direction to the left, just to be different. Let's imagine that this ship is heading away from the Earth in the positive x direction with a speed of 0.600 c. So in terms of relative velocities, the velocity of the ship relative to the Earth has an amount 0.600 c, and it's in the positive x direction. Let's imagine that the Earth fires a missile after the ship. So again, this is all in the positive x direction. The velocity of the missile relative to the Earth is positive 0.900 c. So remember, away from the Earth to the left is the positive x direction. So naturally, we might want to calculate the velocity of the missile relative to the ship. How fast is the missile closing in on the ship? Let's first try to imagine the sign of this answer. Relative to the Earth, the missile is heading away from the Earth faster than the ship. So the ship and the missile should relatively be getting closer together. From the ship's perspective, the missile's closing in from the right toward the ship. That means the missile's heading to the left. That's in the positive x direction in this coordinate system. So the velocity of the missile relative to the ship should come out positive. All right. If this were just Galilean, if we tried to use the Galilean relative velocity formula, we'd get the answer of it's closing in at point 300 c. That's going to be the numerator, but the denominator, right, will change that. So we can't just take these numbers and add them or subtract them as we would with ordinary, everyday, a few meter per second velocities. We've got to use the full-blown Einstein formula because these are an appreciable fraction of the speed of light. All right, so here we go. Again, as in the first example, I'm not going to try and figure out which thing is A, which thing is B, which thing is D, and do some mapping. I'm going to use this and say, okay, if I want the velocity of the missile relative to the ship, I'm going to have two velocities in here. I'll just put them here. I'll add them. The first subscript here has to match the first subscript here. Of course, I'll leave room for the second subscript. And the second subscript for the second velocity is the second subscript here. So I'll have box, because there's the linkage, and then ship. And then I'll have all of this appearing again in the denominator, 1 plus over c squared of the first velocity multiplied by the second velocity, whatever those turn out to be. Okay, now I got to identify my third object. In this problem, I've only got one third object, so I'll put the Earth there. But it could have been anything else. If I know the velocity of the missile relative to some other third object, the velocity of that third object relative to the ship, it wouldn't matter. So I might have multiple objects in my problem. All right, so let me put these in. Velocity of missile relative to Earth, velocity of Earth relative to ship, and then we'll work this out. And again, all these are, you can only use this formula if everything is aligned up in some coordinate axis. If things are in different x, y, z directions, there are different formulas for each component. Okay, we're only going to work in one dimension. So let's plug numbers in. Velocity of the missile relative to the ship. All right. First, velocity of the missile relative to the Earth. I have that. That's positive 0.900 c. Then the velocity of the Earth relative to the ship. Well, I don't have that. I have the velocity of the ship relative to the Earth. That's positive 0.600 c. What I want is the velocity of the Earth relative to the ship. That's going to be negative 0.600 c. All right, so this and this, the subscripts are switched, so this is going to be the negative of that. And that's what I've got there. That's why I put it in red. All right, then in the denominator, I've got 1 plus, I've got my c squared. I'm not going to put all the zeros. I've got my first velocity here, so 0.9 c. My second velocity, minus 0.6 c. Let's work out what that is. So plus 0.9 c plus a negative 0.6 c gives me plus 0.300 c. And then in the denominator, let's work with this over here. C times c divided by c squared is 1. So then I'm going to be left with 0.9 times 0.6. That's minus 0.54. 1 minus 0.54 is 0.46. And so I can work that answer out. That's going to equal positive 0.652 c. And that, just to make sure I've got it written down, is the velocity of the missile relative to the ship. All right, let's check. Does that make sense? We have a positive answer. That means relative to the ship, the missile's got to be closing in this way, moving to the left, because left is our positive x direction, and that's what we expected, because relative to the Earth, the missile is moving faster than the ship, so it should be closing in. All right, there's other things we could calculate. If the velocity of the missile relative to the ship is 0.652 c. That means the velocity of the ship relative to the missile should be minus 0.652 c. From the perspective of the missile, its coordinate system, and I should have had my x direction pointing that way, the ship is closing in. All right. Ship is going in the negative x direction relative to the missile, right? Because they're getting closer together. So if the missile's fixed in place, the ship is heading to the right, and that's the negative x direction, all right, from in the missile's coordinate system. All right, so hopefully these examples help illustrate how to use the relative velocity formula, Einstein's relative velocity formula. I want to emphasize again, this formula is general. It works for speeds from 0 meters per second all the way up to the speed of light. All right, so even though we only usually break this out when we have speeds that are appreciable fraction of the speed of light, it still works for all the speeds that the ordinary, everyday Galilean velocity formula works for. It's just more complicated. Remember, the ordinary velocity formula for low speeds is just the numerator of this greater formula, but the denominator makes this thing general. All right, thanks for watching.